Today we want to put our parameterized curves into some environment where we can actually make some calculations. We started describing our parameterized curves with vectors. This was useful to describe each of these points with some vector. So this point, that will do. So that the point on the curve is described by some vector, r of t. So that r of t will be describing some point on this curve. We could think of, if the origin is, wherever the origin is, we could think of r of t as describing all these vectors, but it's still just tracing out this path in R3. So r of t is just going to be a location. And then we saw yesterday that if we took the derivative of each of the components, we would find that v of t, our velocity vector, is tangent to r of t. So it's r prime of t. So that's the direction where things are headed. So we've taken parameterized curves and we've put our, parameterized curves, a one-dimensional curve in R3, and we've started to install our derivative thinking on it. So if we imagine that one of the discussions from a couple of days ago was to look around the world and see a parameterized curve, and then think about what the derivative is going to tell us. And then the derivative could tell us what direction we are headed at any given moment. So if this is a bird flying around or a fly flying around your room, because we don't go outside anymore, or a plane flying through the air, which is going all crazy like this because we probably shouldn't be flying places. I'm just kidding. There are important things like baseball games going on. I guess those are over now. There are really important things like football games that are going to be going on. So, whoa. And the derivative thinking is just what direction are things going? And so that will be a vector tangent to the curve, pointing where things are headed next. And then there will be some acceleration. In this case, it looks like the acceleration will be pointing this way because it's going to pull this velocity vector. And then it looks like our acceleration is going to start pulling this other direction, so the velocity vector will want to turn back. So we're imagining this one-dimensional path running through three-dimensional space. We're imagining derivatives on that space, derivatives tangent to that curve. And we can even think about acceleration. So all these points on this path, these are all just going to be vectors. Let's take this curve and put it in and add some stuff to the space around it so that we can make some vector calculations that we can then add up. So now we need a place to put our parameterized curves that are going to be vectors, and we're going to look at vector fields. Right. A vector field is just a function that assigns to each point in space a vector. So it's a function whose output is a vector. So a vector field is a function where the output is a vector. And we're going to start by looking at R2 or R3. But to each point in space, the vector field assigns a vector. So let's look at an example of a vector field, what it would look like. So for example, this book always uses capital F for its vector fields. So I'm going to name the function, I'm going to name our function capital F, and I'm going to indicate that it's a vector field by saying this is a vector. But I'm still going to have inputs, say like x, y. So this function is assigning to each point x, y a vector. So the output needs to look like a vector. And the x and y are going to both be x and y are going to, sorry, the I and j components are both going to have functions of x at each of those points. So let's start with the classic example. Let's start with a different classic example. What do I want to do? How about minus y times I plus x times j? I'm thinking that this is probably the first example. This is going to make a nice circle. So to each point xy, we're going to assign this vector. Input a point in R2, output is a vector in R2. So let's try to sketch this vector field. So if we pick some points at, say, the point at the origin, we're going to get 0i plus 0j. So we're going to get 0 at the origin. That was exciting. Let's pick another point. Let's pick the point f of 1, 0. Let's cruise along the x-axis and see what kind of vectors we're going to get. So f at 1, 0. So y is 0, so 0i plus 1 times j. So at the point 1, 0, let's be realistic. At the point 1, 0, I'll draw the vector 0i plus 1j. Let's plot another vector. So rather than plotting some height above the xy plane, where z is a function of x and y, in the xy plane, I'm drawing a vector at every single point. So let's plot the vector at 2, 0. So y is still 0, and the j component is a 2. So we get a longer vector. Now, if we plot vectors on the other side, if I look at vectors at, say, -1, 0, I'm just looking at the x-axis for now, we'll get y is still 0, I, minus 1 times j. So at -1, 0, I've got a vector pointing the other direction. Same length as this one, but pointing in the other direction. Then if I go to the next point, f of 2, 0, I'll get 0i minus 2j. So now I'll have one that's longer. So now I have a mirror on the other side. So along the x-axis, we get all these vectors that are pointing up on the positive x-axis, and they get bigger as we go further away from the origin. And then on the negative x-axis, we have a similar thing. So what this indicates is that the origin, it's kind of like these vectors are trying to turn the x-axis around. That's the way we want to see, what we want to see in these vectors. Initially, once we get off of the x-axis, then we're going to be going in a different direction. But initially, this is what the vector field is doing. It's pulling the x-axis in a clockwise direction. Any questions? So if we start calculating some more vectors, let's cruise along the y-axis. So let's go along the y-axis. I use green. Oh, those are the in-between ones. So let's look at f of 1, 0. That's the one we just did. In my mind, I said turn 1, 0 around, and I started writing when I was thinking turn 1, 0 around, and so I just wrote 1, 0. Good job. Is that a more coffee problem or a less coffee problem? So let's look at the point 1, 0. Be about right there. Now, in this case, y is 1, so we have plugged that into the function here. So minus 1 times I plus 0 times j. So now we're getting no movement in the y direction. We're getting movement in the x direction. So this vector is going to be negative 1i plus 0j. Then if I plot the vector at 0, 2, we'll get negative 2i plus 0j. We'll get a vector twice as long, but going in that same direction. Any questions? And then we're going to do a similar thing down here. If we plot f of 0, negative 1, we'll have a vector going in this direction. 0, negative 2, it'll be twice as long going in this positive direction. And so what we should see is that we've got this motion kind of going around in a circle, where we'll have a 1 in between here at 1.5, and a little shorter one. So what we see is that the x is, in the x-axis, it's kind of pulling around. I have a clear ruler. Why don't I use that? The vector field is kind of pulling the x-axis this direction. And on the y-axis, it's pulling this direction. So what the vector field is describing is motion that's kind of going in a circle. Let's think about some more points. If we think about along the line where y is equal to x, if we plot some points here, so let's say we calculate along this line y equals x, the vector at 1, 1. The vector at 1, 1 will have negative 1 for y, so negative 1i, plus 1 for j. So at this point, 1, 1 will be going in negative 1, 1 direction. So we'll be going perpendicular to this y, the y equals x line. And then at 2, 2, we'll have a vector that's just doing this twice as much. So we'll be going at negative 2i plus 2j. So in the negative x direction and the positive y direction. And if we think about the vectors in the middle, so what we're doing is we're really starting to see that this vector field is going to produce, looks like it's going to produce some kind of circular motion. Any questions? So maybe this vector field is suggesting some kind of circular motion, counterclockwise circular motion. The vectors suggest counterclockwise circular motion. We can imagine if we start here at 1, 0, we're going to go up a little bit. And then once we're up a little bit off of the x-axis, we won't be going vertically because our y-coordinate is going to push us. Our y-coordinate is going to, our x-coordinate is going to, our x-coordinate is going to start decreasing because our x is going to start decreasing. And it's going to be less pull up, and we're going to start pulling to the left. So it's going to start pulling us around in a circle. Any questions? All right. So what we want to do is to each point in space, either R2 or R3, could be bigger. Let's start with R2 and R3. We're assigning a vector. Let's pause the video here and look at another example.